Every day, our planet is bathed in the light of an unyielding thermonuclear inferno. The Sun. It burns roughly 1.3 million times larger than Earth. It grips the entire solar system with its massive gravity. But sharing our local space is the Moon, a cold rock just 1/4 the size of our own planet. Occasionally, a bizarre alignment occurs. That tiny rock travels along its orbit and steps directly in front of our colossal star, casting a dark shadow backward into space. Down on Earth, the physical effects are immediate and visceral. A wall of darkness races across continents at supersonic speeds of 3,000 kilometers per hour. Midday instantly turns to pitch black night. Stars emerge in the sky, and temperatures plummet. How does this geometry actually work? The Sun is millions of times more massive than the Moon, yet from our perspective on the ground, the tiny rock manages to completely block out the giant. To understand the physics, we can look at this geometric diagram of shadows. When the Sun's light hits the Moon, it creates two separate shadow zones. The first is the penumbra, a wide, translucent outer cone. If you stand inside this zone on Earth, you experience a partial eclipse, where the Sun looks like a glowing crescent. Deeper inside lies the umbra. This tight, dark inner cone is where 100% of the Sun's light is blocked. It only touches the Earth's surface in a narrow path, usually 100 to 200 kilometers wide. Standing inside this specific band is the only way to experience totality. Here is a model comparing their physical scales. The Sun has a massive diameter of roughly 1.4 million kilometers, while the Moon is only about 3,500 kilometers across. That means the Sun is roughly 400 times wider than the Moon. By sheer statistical coincidence, the Sun is also roughly 400 times farther away from Earth than the Moon is. Because angular size depends on both physical dimensions and distance, these two measurements cancel each other out. In our sky, they both occupy roughly 0.5 degrees of visual arc. If the Moon were even slightly smaller, or if its orbit were slightly farther away, that precise overlap would fail, making total solar eclipses physically impossible. If the Moon completes an orbit around Earth every 29.5 days, logic suggests we should see a total eclipse every single month, when the Moon passes between us and the Sun. Yet, we don't. This diagram illustrates why. The flat grid represents the ecliptic plane, which is the path Earth takes around the Sun. The ring represents the Moon's orbit, which is actually tilted by about 5.1 degrees relative to the ecliptic. Because of this incline, the Moon usually passes too high or too low. Most months, its shadow completely misses Earth entirely, sailing harmlessly over the North Pole, or dipping far below the South Pole into empty space. The two specific points where these orbital paths cross are called lunar nodes. An eclipse requires a perfect straight-line alignment of the Earth, Moon, and Sun, a configuration known as syzygy. This geometric lock only happens when the new moon phase perfectly aligns with one of these nodes. The Sun's gravity slowly tugs on the Moon's orbit, causing these nodes to wobble and rotate over time. This creates the Saros cycle, a highly predictable 18-year rhythm where nearly identical eclipses repeat across the globe. Looking at this 4-panel breakdown, we can see how the Moon's elliptical orbit alters the event. When the Moon is at perigee, its closest point to Earth, it appears large enough to create a total eclipse. When it's at apogee, its farthest point, it appears smaller, leaving a ring of sunlight exposed in an annular eclipse. Off-center alignments create partial eclipses, while rare variations in Earth's curvature produce a hybrid event. For observers standing directly in the path of totality, the physical event unfolds over roughly 2 hours. It begins with first contact, as the edge of the Moon takes its initial bite out of the solar disk, slowly marching toward total coverage. Just seconds before the Sun disappears entirely, a single burst of intense sunlight piercing through a deep valley on the lunar horizon, paired with the glowing sliver of the remaining Sun, it creates a brilliant flash known as the diamond ring effect. Immediately following this flash, the last remaining rays of light filter through the Moon's rugged topography. Because the lunar surface is covered in jagged mountains and ancient craters, the light fragments into isolated, shimmering droplets, known as Bailey's beads. By carefully timing how and when these individual beads of light vanish, astrophysicists can calculate the exact depths of lunar valleys, mapping the moon's 3D surface topography in real time. Then, the final bead vanishes, and the blinding surface of the sun is fully blocked. In the sudden twilight, the solar corona emerges. Ghostly white tendrils of superheated plasma stretch millions of kilometers into space, while loops of bright magenta gas, solar prominences, flare off the edges. The intense glare of the sun normally hides these structures entirely. A brief alignment of a tiny rock blocking that glare provides the only natural opportunity for human eyes to observe the superheated, secret atmosphere of our own star. While observers watch the sky, the local environment on the ground reacts drastically. The sudden loss of solar radiation causes the air temperature to plunge by 5 to 10 degrees Celsius in a matter of minutes. This rapid cooling triggers severe atmospheric pressure drops, killing local breezes in a phenomenon known as the eclipse wind. The sudden plunge into darkness also hijacks the circadian rhythms of local wildlife. Fooled into thinking night has arrived early, diurnal birds retreat to their roosts to sleep, while nocturnal crickets and insects emerge to chirp in the middle of the day. But this astronomical spectacle has a strict expiration date. Earth's oceans bulge under the gravitational pull of the moon. The friction from these moving tides creates drag on the Earth, slowly applying the brakes to our planet's rotation. As Earth slows down, orbital mechanics dictate the moon must gain that lost energy. As a result, the moon slowly spirals outward, drifting away from Earth at a rate of 3.8 centimeters every single year. As the moon drifts farther into deep space, its apparent visual size in our sky gradually shrinks. In roughly 600 million years, it will appear too small to cover the sun entirely. The era of total solar eclipses will permanently end, leaving our distant descendants with nothing but annular rings of fire. We happen to exist in a brief cosmic window, enjoying a perfectly timed planetary clockwork that reveals the hidden dynamics of our solar system.